Good morning and Happy New Year to the audience joining us online. This is Jeff Pontius, Engineering Director of Brake R&D for HL Mando America, and I'll be the moderator for today's webinar. Today, our speakers will share their expertise and insights on the future of brake systems, electromechanical brake, or EMB. Today's session will consist of opening remarks from our CEO, a 30-minute long presentation with 4 major topics related to EMB, and approximately 20 minutes of Q&A. For the Q&A portion, there are 2 ways for you to actively participate in a confidential way for your convenience. First, you may ask your questions freely by using the chat window. Your name will be kept private and confidential. Second, any unanswered questions will be addressed by the HL Mando experts with answers distributed after the conclusion of the presentation. Now, please welcome Steve Cho, the CEO of HL Mando, for his opening comments.
Good morning and good afternoon to the audience joining us online from around the world. This is Steve Cho, CEO of HL Mando. I'd like to thank everyone who joined this online conference to hear and share great ideas and innovation about future mobility technology, especially in the area of motion control. As many of you already know, HL Mando specializes in xEV and autonomous driving solutions, including brake, steering, suspension, drive and traction, and power electronics for light vehicles, as well as different types of mobility, including micro-mobility, robots, and more. HL Mando has been in the vehicle chassis business for more than 60 years. During that time, working together closely with many OEMs globally through shared experiences and expertise. We have built a strong foundation to enable our mutual success. As the industry and technology continue to dramatically change, we have been closely collaborating with our customers and partners to transform vehicles to mobility that is electrified and autonomous. Imagine every move. That is what HL Mando ultimately envisions, and that is the key message for CES 2023. With HL's technology, every move you or the world make can and will be safer, greener, and easier. Today, our speakers will share their valuable expertise and insights on the future of brake system, which is electromechanical brake system. I hope this conference will trigger your imagination and innovation. Thank you very much.
Thank you, Mr. Cho, for your opening comments. Now we will go through today's 4 technical topics one by one. Hello, my name is Jeff Pontius. I'm the Director of Brake Engineering here at HL Mando. Today, we're going to talk about electromechanical brakes, and specifically, I'd like to start with what is EMB. EMB, or electromechanical brake, is the next step forward in technology and braking systems and components. Working in cooperation, HL Mando with HL Mechatronics have designed an electromechanical brake that is a fully dry brake caliper. HL Mando's EMB design utilizes proven technology from within HL Mando's brake and steering products' core technologies, and can be utilized as either a 2-channel or 4-channel configuration depending on the customer's specific application. Utilizing a brushless motor and an onboard ECU, individual wheel end control is possible. Either full ABS ESC at the wheel end or first slip mitigation and handoff to a centralized domain controller is possible. Under development for 3 years, the design has successfully completed a full bench and dynamometer DV, along with thousands of miles of on-vehicle development. The first analog brake systems were introduced in the 1930s, but were not 100% installed to vehicles in the USA until legislation enacted in 2007 required their inclusion. Today, even with the widespread availability of vacuumless boost technology, such as Mando's IDB line of products, which combine the functions of the traditional booster, master cylinder, and ABS ESC control module into a one-box solution, some automakers have not yet introduced this technology. This is to say that sometimes technology is slow to be introduced in brake systems. Furthermore, there have been numerous past attempts by brake component manufacturers to introduce new brake concepts, including electromechanical brakes. So one may wonder or ask the question, why now? There are two main topics I will touch on regarding why now is the right time for EMBs. The first are the enablers, and the second are the advantages. There are several key market shifts at a vehicle level that enable the introduction of EMB at this time. The main market shift is the electrification of the vehicle powertrain. As we know, multiple car manufacturers have already made pledges to convert their entire vehicle lineup from ICE to BEV vehicles in the next decade. Others have pledged conversion of a high percentage of their vehicles to BEV or alternative fuels within a similar timeframe. This trend is easily observed with several significant BEV vehicle launches having already occurred and dozens, if not hundreds of others under development within car manufacturers globally. A second major change is the introduction of new technology for other safety critical automotive components, such as electrical or steer-by-wire and autonomous driving features. What these two market changes have in common is that they combine to lead increased vehicle sophistication and, more specifically, redundancy in the vehicle's electrical architecture. This topic will be discussed in greater detail in a few minutes, but from the safety perspective, the redundancy or the backup or secondary electrical system in the vehicle electrical architecture is the key enabler to EMB introduction at this time. Now speaking about the advantages. There are many advantages to the HL Mando EMB when compared to a conventional brake system. Some of these advantages will be transparent or not easily recognized by the driver or passenger of the vehicle, but offer other advantages. Some of these advantages are lower brake drag, leading to improved fuel economy or battery mileage, the elimination of brake fluid from the vehicle. This alone has many benefits. Elimination of hydraulic lines from the vehicles. Hydraulic line corrosion has been a problem on some vehicles in the past, and hydraulic connections are known to be a slow manufacturing and high DFMEA failure mode operation. Elimination of brake evacuation and fill issues and associated repairs at vehicle assembly. Elimination of caustic and flammable fluid from the vehicle. Improved environmental sustainability. Elimination or lack of recycling of fluid at repair or end of life. Decoupling of the pedal for regenerative and autonomous driving. Compact package similar in size to existing MOC calipers. Flexibility in parking brake function integration. Can be easily applied to two wheels, either the front or the rear, or four wheels, depending on OEM and vehicle needs. Decreased stopping distance due to decreased time to response of electrical systems compared to hydraulic systems. Robust integrated parking brake function, ideal for vehicles with CVTs or with no parking poles. Besides the above items, it is anticipated that there will be new value-added features that HL Mando and customer engineers will be able to take advantage of as EMB is applied to new vehicle platforms.
Hello, my name is Kate Hurtubise, and I'm a system safety engineer at Hala Mechatronics. Hala's EMB system architecture is designed to be implemented with vehicle-level dual power supplies and dual vehicle-level brake control units. The independent power at each controller allows prevention of single-point faults from degrading the system. Each BCU sends commands to all four corners, and the commands are allocated as primary or secondary based on a diagonal split design. Independent EMB controllers are at each corner. In addition to applying the prescribed clamp force, they also are each electronic park brake capable and wheel speed compatible. This redundancy prevents single point faults from multiple systems, from power supply and from vehicle BCU faults. The safety requirements have been implemented from multiple regulatory requirement sources and also in accordance with ISO 26262 specifications. These safety requirements are evaluated according to vehicle-level safety goals from multiple OEMs. Per ISO 26262 specifications, each safety goal is analyzed by deriving a qualitative FTA. In addition to the OEM and regulatory specified requirements, additional safety requirements are identified through this fault tree analysis. These safety requirements are considered at both corner level and vehicle level and traced to the safety goal. PALA is also targeting regulation compliant performance requirements, deceleration metrics for each fail functional configuration of the vehicle. Control strategies have been derived for each variation of fail functional operation as shown below.
Hello, my name is Jeremy Dobbs. I'm a controls engineer at HL Mechatronics in Bay City, Michigan. And today I'm going to be talking about the advantages that digital twin models bring to the development of safety critical components in automotive systems. So just wanted to start by explaining what a digital twin is. So a digital twin is a model of a physical system that emulates important features of it. So basically the key dynamics of the system and software behavior, and is interface compatible with the physical system that it will be integrated into. So in case of our electromechanical brake or EMB, this would include being compatible with the communication bus, electrical power bus, and mechanical interfaces of a virtual vehicle platform that it could be integrated into. So this cross-domain model includes the mechanical, electrical, thermal, and software behavior of the system that we're trying to model, and it allows for a virtualization of functional testing of the system, calibration, and feature development as we're exploring new features that the system could have. So in the case of the automotive industry, when we talk about a digital twin, on the OEM side, this would include a complete vehicle model. So it would include, in many cases, models of the different control units that are in the vehicle that are delivered by tier 1 suppliers. So for example, the brake and steering systems. Models of components that are owned by the OEM, so like the powertrain, and then typically a co-simulation with a vehicle dynamics tool like CarSim or CarMaker. Then on the supplier side, so these models that we deliver to the OEM would include a plant model of the system dynamics of the mechanical design, a model of the full software stack of the system where the fidelity of that software model would be fit to meet the application. So this could go anywhere from all the way down to the embedded registers of the actual microprocessor. So this would be like a virtual ECU model, to something higher level earlier in development that would be more like an algorithm level model of the behavior of the system. And then additionally, this model will include the hardware models of the electrical components that are key to the system's behavior. So for example, things like the motor drive circuitry and interfaces with any of the sensors. So why do we want to create digital twins? So the main driving factors are that it reduces development costs and time because it can decrease the amount of prototype vehicles needed in order to go through a full automotive development cycle. Basically, more and more of your integration testing can be done in a virtual environment, and you can find issues and correct them before they actually get to the vehicle. So it allows us to do virtual trade studies where we can rapidly iterate over different design concepts without having to build up hardware. And it increases the efficiency of the development process because we're spending less time actually ordering tests or doing tests ourselves, and more time on solving the engineering problems. So it simplifies the root cause analysis of the system. So basically we can find defects in our design earlier in development, preferably before they actually reach the customer. And on the OEM side, they're able to perform integration testing between their different subcomponents earlier in the development cycle. So things like the communication between different electrical components in the vehicle can be tested in a virtual environment before the hardware is actually available. And OEMs are rapidly adopting virtualization requirements for all electrical tier 1 suppliers. So HL Mechatronics has been working with OEM partners to help define this process. We've been in discussions with the OEMs that we work with on what the right process is to follow this, how we can integrate these models through the entire V cycle to ease our development. So, and I just wanted to give an example specifically of how digital twin models can be applied to EMB systems. So this is just showing sort of what the model looks like, where there's a multi-domain simulation of the braking actuator, where there's a calibration file that could be actual calibrations for the brake from the hardware that are loaded into the model, a model of the software, electrical hardware, and mechanical plant that are all interfacing with one another in real time. And then the interfaces basically in and out of the model would include the communications, electrical interfaces, in the case of the EMB, a wheel speed signal coming from a sensor model. Then the outputs would be the current draw that's going on to the electrical bus so that we can predict basically our power loading, temperatures so that we know where we are thermally with the design, and then the actual clamping force output of the system, since that tells us how we're doing with our performance requirements. So EMB is in a position where it's uniquely suited to take advantage of digital twin development because it's an emerging technology, which means that there is a great need for rapid trade studies and design iteration as the technology advances. So this virtualization is allowing us to keep up with the customer demand for EMB development. So in conclusion, digital twin models are going to be required to meet OEM virtualization requirements. And HL Mechatronics is a leader in this area. We have in-house expertise in the design and modeling of many cross-domain areas. So power electronics, motors and sensors, software, mechanical actuators, mechatronic integration, and just in general steering, brake, and propulsion technology. And digital twin models reduce development costs and time and reduce the need for hardware testing.
Hi, my name is Raja Ravi Ramakrishnan. I am Chief Scientist in the controls area at HALA Mechatronics. So we are responsible for controls development for various products. And what I'm going to talk today is about advantages and challenges for EMB controls. So this slide shows an architecture of a brake-by-wire or EMB system, where you can see that the actuators and the motor is attached to all the four wheels. This kind of architecture for EMB provides a lot of flexibility in especially in vehicle controls while stopping and how to maneuver the vehicle. It also gives us another aspect of it is what we call for safety, which is what we call as redundancy, because these actuators are similar and each actuators are placed in different wheels. So it give us a redundant and architecture where we have multiple actuators trying to control the vehicle. So from a safety architecture and as well as from a performance perspective, EMB takes a whole new domain of braking architecture for the future automotive. Now, what are the key advantages for EMB control? Why do we have to go for EMB will be the next question, which I'll be trying to answer. The main advantages is, as you see here, increases the safety by decreasing the stopping distance compared with pure electric braking. With EMB, as the motor is reacting, it's much faster compared to a hydraulic system trying to stop the vehicle, and you can actually decrease the stopping distance because of the actuation time and also by improving the amount of force applied to the brakes. The other key aspect of EMB control is the undesirable feedbacks in hydraulics. I think everybody who have driven the hydraulics braking would have seen some undesirable pedal feedbacks while it going through potholes, or whether you're braking too fast, you can see an undesirable feedbacks in hydraulics. In EMB type systems, such feedbacks can be better managed, and a driver experience for a better feedback mechanism can be given. A driver actually can have a better feel of controls of the brakes. So such high level of automation or high level of control of feedback allows this EMB control to be superior compared to what today's hydraulics braking is. The other key technical area where EMB is performing better is the active gap control reduced during drag or brake pad wear, which reduces the brake pad wear. So if you see it, the active gap control reduces due to the active gap control, we can reduce the amount of brake pad wear and the drag applied to the pads. And therefore, the maintenance of pad wear and can be adjusted and it can be improved compared to the today's normal hydraulics braking. And especially during an emergency kind of braking, the amount of force we apply tends to be controlled, where EMB can control the accurate amount of force we need to apply, thereby eliminating overstressing or understressing the pad. The other key area is also what we call as better control of all the brakes with respect to the driver's intention. Now, in EMB control architecture, as I showed in the previous slide, you would have seen that the driver intention is actually captured, and we can actually give the right amount of force needed for the brakes so that we can actually maintain the pad wear as well as provide a better control of the brakes. Thereby, his intention can be clearly understood and we can provide the accurate response from a brake perspective. The other final advantage we would see is the driving comfort can be increased by reduced pedal force, especially with different type of drivers and with a different amount of force. We need to provide a better user friendly, where lower pedal force are needed to provide larger braking force. We can adjust the tuning. So that is a key feature when we go into EMB. We can actually adjust the tuning, just like steering is today, where we have different types of tuning, like sports, comfort. We can have different types of tuning pedal force and tunable pedal feel also. So the driver amount of force they need to apply can be tuned, and also how much they are able to feel back can also be adjusted. Such great tunability and experience in EMB provides a huge advantage compared to the hydraulics braking, which we are having today. Now, the advantages clearly seen in the previous slide shows a huge advantage why the market is moving towards EMB and why there's a huge push for this new technology. in industry. But is that without any challenge? There are many challenges to overcome. And this slide kind of provides the main challenges we are trying to overcome in this technology. As you know, now that there is no mechanical or physical hydraulic connections between the pedal and the brake, this requires safety, and safety is the key in all of these. This requires, therefore, high redundancy to make sure upon a failure that the system shall be capable to perform. It's a very key point because we don't want one brakes to fail all the brakes and the system is without any braking control. So therefore, redundancy is a key aspect. This requires high fault tolerant communication hardware. The redundancy doesn't just stop by motor. It is in the whole system architecture design when we are doing it. So this requires high fault tolerant communication hardware. Key redundancy is most of the sensors and actuators which are used, that is including the motor, the position sensor, the current sensors, and any other sensors we are trying to use for the controls. We need to have redundancy in that. High speed fail-tolerant communication hardware between various ECUs. Remember, there are multiple ECUs communicating with each other for the whole system to work. So we need a high tolerance system, fail tolerant, so that the communication hardware is good and we are able to communicate between ECUs too. So that is a very key area, and which is a highly developing area in automotive. Moreover, going to EMB has a specific advantage, especially when the automotive is going towards electrical vehicles, and that is using high voltage chipsets. To take the full advantage of the advanced vehicle power architecture, as you guys all know, that with electric vehicle, the voltage level has bumped up, and we can take the advantage of using that high voltage in our high voltage chipset development and use that for EMB. So it need not be a low voltage system. It can go up to like 48 volts kind of system, but we can take advantages of such architecture now. Now, high redundancy in sensors, which I brought about, and power chips and microcontrollers, which is used, increases the cost. So it is very key that in order to provide a viable solution for the market, we need to have smart solutions for the redundancies. Thereby, we are not increasing the cost, but we are able to manage redundancy by keeping the cost at the right ratio so that we can actually sell these systems. So that is a key challenge. High redundancy requirements means higher end MCUs are needed for applications. That means we need a better MCUs which can perform at higher rate. Software needs to power to execute new safety functions. So software speed and the redundancy in the dual controllers needs to be evaluated so that we can run higher, faster diagnostics and higher safety functions, such that it can not only provide the amount of safety required and mechanism required to know the issues, as well as provide diagnostics. And also, we also need software to be performing without any throughput issues. So we need higher end MCUs for that. High degree of availability of the complete system is required. Therefore, since there's no mechanical feedback in such systems. So for this EMB to work, we need to make sure that the complete system architecture there's high degree of availability. That means when I say availability is that, say a sensor failure happens, we are not bringing down the system. We are still performing with full performance after a single point failures. So we need to understand how well we can provide the performance of the system even after failures. How well can the architecture provide full performance even after a single point failures? Now, we are even talking about dual point and triple point failures to make sure that there is adequate performance levels in these actuators so that systems can be brought to the safe place or safe zone or safe area, what we call in industry, when even after a failure happens. So high degree of availability in such architectures are key. So these are design constraints, are design decisions we need to make when we develop these systems. Another area we are keenly looking at is the software systemic failures. That means a systemic failure is key when we analyze safety now, because a systemic failure can bring down, with one fault, system can bring down the whole other systems too. So such as erroneous MCU behavior needs to be addressed, and such fault mitigation in the total system failure even with redundancy, should be addressed, and make sure that such systemic failures are addressed before in the design. Thereby, in production, there is no such issues, and the user doesn't have to have a systemic failure at all. Such key areas have to be understood, need to be root caused, need to be developed such that systemic failures are avoided, or we have a plan, even if the systemic failure happens, that we provide adequate power to the system so that the system can be brought to the safe zone. Now, so my last slide, why HL? Why we should go with HL for EMB? What is our expertise? And this really lies with what we do today as a core. HL is trying to are the first expertise in first fully redundant production steering system. We have developed the first productionized fully redundant architecture for steering systems, which gives us the biggest background or biggest base to go and develop such highly redundant system, and how to make it practically possible for productionizing, and how to make sure the cost is not high, but still provide the full safety. So we have a good expertise in that area because we have developed the steering system with fully redundant architecture. So we are taking that, and that is a huge background we have to make sure we are developing the right EMB architecture. Expertise in fully redundant IPMSM and PMSM motor drive. We are experts in motor drive architectures and give us full redundancy. That means even after a sensor failures, we are able, even after a single point failure in any of our architecture, which includes sensor, power electronics, and motors, we are able to provide full architecture, full performance. So we have systems already developed which can provide a full performance even after a first point failure. We are also developing systems which can provide adequate performance even after dual or triple point failures. Expert in doing this needs, in order to develop such architectures, we are expert in doing such safety analysis for such complex systems. That is a huge area of technical development where we analyze the safety even before the designing the architecture. How to analyze that safety for such complex system to understand the single, dual, and latent point failures. We are expert in that, and that's how we developed our first productionized steering system. So we are very good at that aspect. Experting in developing advanced motor controls, including systems with low torqueable with active cancellation. This is a key in areas like steering and brakes, where we can still use IPMSM drive systems. As you all know, IPMSM drive systems inherently has a lot of torque ripples, and the performance are bad because they use less rare earth magnet, and thereby we can reduce the cost. But how do I productionize so that the performance is good? We have active torque cancellation techniques, which we already developed and applied in steering systems, which we are also trying to incorporate in EMB, thereby providing a very good performing systems and very good low torque ripple systems, even with IPMSM drive systems. Thereby we are reducing the cost in the motor because it has less dependency on rare earth materials, and also, but still performance is not mitigated. Performance is not reduced. We are still having high performance with such active cancellation technique. We have also demonstrated, especially for EMB, how to have high bandwidth force control system, especially in the areas of ABS, and improving much. It's actually better than the present hydraulics ABS, how we can improve because of a high bandwidth force control mechanism and high response in force control. So all these aspects, which are key for a good architecture for EMB, we are expertise in that, and we have actually shown the solutions even in steering systems, which we are taking over towards EMB to provide a better performing, safer, and highly performing systems for meeting all the OEM's requirements and needs for a good performing EMB architecture. Thank you. I thank all the people for our presentation, and I really thank you for listening to this. Thanks a lot.
Thank you, Kate, Jeremy, and Raja for your informative presentations. And thank you to our guests for your attention during those presentations. Now we will begin our Q&A session. If you've not already done so, now's the time to please feel free to use the online chat function to submit your questions. And as a reminder, those are confidential. Your name will not be shown to anyone else in the chat function. I see we already have a few questions at this time, so we'll go ahead and get started with the Q&A. Here's our first question. What improvements will EMB bring to the vehicle and end user? Raja, if you don't mind answering that question, please.
Yep, thanks, Jeff. So from an user perspective, one of the advantages you have in EMB is having a better feedback mechanism that can be tunable too. From a conventional braking point of view, this tunability features and how much the driver feels back, it can be adjusted and tuned to, which is a great advantage from an end user perspective. So that is one of the key advantages you get while using in the EMB architecture. And especially one other advantage you see that since we have controls of each individual corners, from a vehicle dynamics perspective, we can better control the vehicle also. So that is from the EMB architectural, so we tend to get that kind of a advantage point. From a vehicle perspective, also, if you look at it, since the architecture-wise, we are actuating each corners, there is inbuilt redundancy kept in these systems, and therefore, from a safety aspect, also we can have a heterogeneous redundancy kind of a systems too, which can be developed for EMB architecture. Moreover, as I talked before in the presentation too, there's from a gap control perspective, from the wear perspective, we can control the amount of wear and minimize that so that the operating cost is low. So those are the additional features you get from EMB. Thanks.
Thank you for that response, Raja. Our next question is, what impact does EMB have on the environment and sustainability? And if the team doesn't mind, I'll take that question. EMB will have a very significant impact on the environment and sustainability. The HL Mando EMB is a completely dry product. There's no brake fluid required in the system. This eliminates a caustic flammable fluid from the vehicle. The elimination of the brake fluid also means that all the associated lines and tubes can be eliminated, including the rubber flex lines from the wheel end. So that is 2 non-renewable resources eliminated from vehicle assembly. This is not just a new vehicle benefit. It's also continues through the life of the vehicle, eliminating any need for fluid flushes, bleeding or refilling throughout the vehicle life, and also eliminates any concerns with end of life having to try to capture and dispose of the used brake fluid. Additionally, as has been previously mentioned, one of the benefits of EMB is the active piston or gap control and the impact that it has on reducing pad drag and overall caliper drag. Reduction in pad drag will have 2 impacts, the first being increased range and mileage of the vehicle, and the second being a reduction in particulate emission from the brake pad and rotor wear, which is a growing concern with pending legislation in Europe regarding particulate emissions. For our third question, it is, how are you able to achieve controlled braking with the loss of one front wheel? Kate, do you mind answering that question, please?
Thank you, Jeff. Our EMB design architecture applies redundant brake commands to independent controllers at each corner. So in the event of a front corner fault, brake force distribution is adjusted at each of the remaining functional corners. So by utilizing chassis level stability control algorithms, clamp forces are applied in coordination with steering and yaw control to meet deceleration targets while maintaining lane. Thank you.
Thank you, Kate. Our next question is, how are digital twins helping drive future automotive development? Jeremy, I think that one's for you, please.
So there are quite a few ways that it's kind of helping with future development. Basically, as we develop these models, it allows us to find problems with our designs earlier in the development process because we're able to do more testing to whatever the product requirements are before hardware is available. and we're able to more easily automate a lot of our testing strategies through the use of these models, especially on the software side. That's really where we'll see the biggest benefits earliest, are that it's relatively, I say easy, relatively easy to have a very high fidelity model of your entire software stack, and test that to requirements and find issues with it without the need for actual hardware testing. And there are many aspects in automotive software that can be tested in an environment like that and give you as good of results as you would get in your hardware testing. And then really that kind of drives that we need less development hardware, less of a vehicle fleet, and we can focus more on that hardware level testing later in the project and kind of be more efficient in the early parts of the project.
Thank you, Jeremy. Here's an interesting question. We may all have slightly different opinion on this one, so maybe I'll have several different of our panel members respond. But the question is, how long will it be until EMB braking is the norm instead of the current wet system? So I don't know. My since I'm talking, I'll say it's a little bit up in the air as it's being driven by customer vehicle application and development, but I think we see some SOPs perhaps taking place in 25 or 26. I don't know if any of the other panel members have any thoughts on that.
I guess I think a lot of it's going to depend on how quickly the electric vehicle actually gets adopted as the main standard. You know, that year keeps changing, but I think it's coming soon, right? So
yeah, thank you. Our next question, apologize while I get so I can see the entire question on my screen. Is the comment on first slip mitigation implying a benefit in allowing corner to do the first clamp force reduction detection, slip based on latencies resulting from communicating with the central processing unit, making it more effective for the corner to handle the first slip based reduction and avoid these latencies? Has this been observed, and is this first slip mitigation an EMB benefit over a central hydraulic brake system, or is it required to be on parity with a central hydraulic first slip mitigation? Jeremy, do you mind tackling that one, please?
yeah, I can take that one. So the main driver for having the first slip mitigation be at the corner level would be to avoid the communication latencies of going back to a central controller. That's correct in that comment. And from what we've observed now, basically with a strategy like that, our first release time would be about on par with what you see in a hydraulic system today. And I think there's room for, especially after first releases, trying to maintain like a constant slip during our ABS profile. I think there's a lot of room for EMB to show benefit over where hydraulic systems are now. But yeah, right now it's been mostly just to avoid those communication latencies.
Okay, thank you, Jeremy. Our next question is maintaining a kiss point torque accuracy from side to side given active gap control a challenge, as current feedback at very low forces seems like would be difficult to use to determine clamp force. How does side to side variation in output torque at low clamp forces compare to central hydraulic systems over the life of the corner? Raja, do you mind tackling that question, please?
Yeah. So I agree that this is one of the challenges we are, but I think from what we have learned is that's where the right algorithms and mitigations like parameter estimations and force accuracy, how do you do at low? these are the algorithms which has to be developed and which has to have fidelity and make sure the accuracy is good. So there are it's a technical good challenges, and we are overcoming those this thing with the right algorithms placed in our drive systems, and also how we productionize these systems so that the part-to-part variations is kept at minimum. Those are the key points which develop in these systems when we develop these, and how to maintain those during production is a key challenge, and that's what we are good at. That's the challenges in these systems. So I think with the right algorithms and the right productionized solutions for all these, and keeping the build part-to-part, keeping that at minimum, how to identify those parameters are key in our technical challenges, which is a good challenge. And that's what we are trying to maintain that and keep the variation at minimum.
Okay, thank you, Raja. Our next question, are the current versions of FMVSS and ECE regulations compatible with EMB, or do OEMs need to apply for any exemptions? Kate, can you tackle that one, please?
Sure, Jeff, thanks. So the current regulations do not account for the advancements that we've seen in technology that will be fully applied with the EMB systems. Particularly the FMVSS braking regulations heavily refer to hydraulic traditional wet systems. However, we have extensively taken into consideration what are the regulation requirements and have been adapting those. But I do foresee in the future either some additional regulations that will be issued specific for the electrical applications and uniqueness of these designs, or further revisions to the current regulations. So that's something that I think we can all expect to see in the future.
Thank you, Kate. Next question, will the average customer see a difference in their braking system performance? Usually not sure who should answer that question. I may add a few comments. We've had a lot of vehicle demonstration rides. As I mentioned in my part of the presentation, we've had over 3 years of winter low mu and high mu testing. And one of the biggest compliments we get, I think, is when customers say that they actually can't feel a difference in the brake system from one vehicle to another. However, I think because of some of the technical advantages that were mentioned by Jeremy and Raja, that we are able to reduce some of the latencies and increase the speed of apply, and we have achieved lower stopping distances compared to the equivalent hydraulic system. I think those are a couple of comments maybe to that question. I don't know if any of the other panelists have any additional thoughts on that question. No. Next question, are there any challenges that are experienced when implementing EMB on an ICE vehicle compared to a BEV?
Yeah, I think I can take that question.
Okay.
I think I would put it this way, is that from a BAV perspective, from an electric vehicle perspective, we can take advantage of that architecture in EMB, because as I said, because of the voltage and stuff like that. So we can take advantage in BEV vehicles. So that will be the key here, compared to being, whether it's more difficult for ICE, I would rather put it in more advantageous to do it in BEV with that architecture BEV has.
Okay, thank you. Let's see. Just looking through the questions. What are the challenges, if any, you see with EMB blending with regenerative braking of EV vehicles in comparison to the current blending methodology with hydraulic brakes?
Just trying to find that one. So I don't think there are any major roadblocks or major challenges that EMB specifically introduces there. I guess the one thing is that the action, depending on the implementation of how it was done on the, for different hydraulic systems, the fact that we're basically that we're using our corner controllers to do the control versus another independent, and then there's another independent controller that is doing the regenerative. That I guess that where that blending decision is made, like in a centralized controller, how that decision is made is something that needs to be come to. But I think the general strategies that are used for hydraulic systems today pretty much carry over.
Yeah, I could add to that a little bit. Also, just to say that with the corner controllers, we do have a lot more flexibility, and to meet the regulatory requirements, there's coordination of the regenerative braking with the ABS functioning. So it does require strong coordination with the chassis level controllers and the corner level controllers, but we're excited to see the flexibility of the system and a lot of opportunity for optimization.
Thank you, Jeremy and Kate. We have a question. How flexible are the EMB designs in the case of packaging? Can the EMB be used for all types of calipers and also for e-drum? I think I mentioned in my part of the presentation that the packaging is nearly equivalent to an equivalent sized MOC or EPB caliper. In fact, it's a little smaller, but we can basically call it the same as an MOC. As far as used for all types of calipers, certainly the design that we've shown is for a typical sliding pin over the rotor collet type caliper. But there's possibility to adapt it to other types of calipers. And yes, HL Mando also has some e-drum technology under development as well. But I think we foresee, at least in the North American market, most of our customers still wanting to stay with disc brakes. But we certainly see that, especially as I mentioned earlier, with the upcoming regulations about particulate emission, some of our customers wanting to re-explore drum brake technology. Check of the time. We may have time for one more question. Let me just scan through the list here, see which ones we've covered. Kind of a couple of questions here that maybe tie together. Do we think we're at a point where the cost of an EMB system is low enough to justify the switch from a hydraulic system? If anyone wants.
Oh, I guess Jeff, do you have an answer for that? You might.
I can, or Jeremy, it's up to you.
No, go ahead.
No, go ahead.
Yeah. Okay. Thanks. Yeah. I certainly think that we're very, very close. We're seeing a lot of interest from our customers. A lot of the cost advantages are actually at the system level, which make them a little harder for HL Mando as a caliper and brake system supplier to calculate. There, as I mentioned previously, a lot of reduction in hoses and fittings. There's going to be some advantages from the vehicle manufacturer side, from a vehicle motion control standpoint. As we mentioned, this is primarily being targeted for BEV vehicles, where our customers are already doing a lot of software integration for the vehicle motion control in the go direction, as I say. So them taking on additional responsibility for the stopping technology is kind of right in line with that, and I think they'll see a lot of synergies. Also, elimination of evac and fill repairs. So there's a lot of vehicle level costs that are hard for us to completely quantify, but based on the customer enthusiasm we're seeing over our product, I think we're there. Okay. Well, just do one more quick check. And if any of the other panelists see any questions that I may have missed, please feel free to speak up.
I guess I saw one question about deriving the clamping force level at the corner. I can give a little insight on that. So
Thanks, Jeremy.
yeah, so our strategy today has been that we intend, and what we've been doing for development is to estimate the amount of clamping force kind of based on our understanding of the physics of the system and the inputs that we do have measurements for related to the motor and its motion and the amount of torque we're applying. So from that in our model, we've developed an algorithm where we can estimate the amount of force at the corner, and we believe that from a cost perspective that is what's required to have a cost competitive system versus the force sensors that are available right now, and that really with the level of accuracy of the force sensors available, that we don't see much, if any, degradation in performance, especially when you consider the variation of the sensors over life and over temperature. So that's the route that we've been taking, and we're continuing to refine it as we get closer to having a production level system. So it's been a very interesting problem to work on, and we're going to keep working on it.
Okay, Jeremy. Thank you, Jeremy. With that, I think we're out of time for any additional questions. I'd like just to take another minute to thank our CEO, Mr. Steve Cho, for his opening comments. And again, Kate, Jeremy, and Raja for their participation and preparing their presentation and taking time today to answer questions. And thank you to all of our participants for their active participation today. We hope this conference will trigger your imagination and innovation. For any questions that we may have missed and could not cover during the Q&A session, we'll send those questions and answers after this through email. HL Mando, imagine every move. That is what HL Mando ultimately envisions, and that is our key message for CES 2023. With HL's technology, every move you or the world can and will be safer, greener, and easier. Anyone who is interested in additional HL Mando technologies, please continue to follow HL Mando during CES and beyond. Thank you very much. Have a good day.